Hello students, welcome back to next unit where we are going to start unit number 4. So here as our first topic, let us see the properties of moist air. So this is the first topic, and then let me introduce the topics which are there in this unit. So the unit title is psychometric properties and processes. And psychometric properties, we are going to see all the topics, all the properties, and then what are the psychometric processes that we are going to discuss. So as first topic, properties of moist air. So this is the first topic we are going to see, and then Gibbs-Dalton law, and it is I will introduce in the first topic itself what is Gibbs-Dalton's law, and then we have specific humidity and dew point temperature, and then we have degree of saturation and relative humidity, enthalpy, humid specific heat and wet bulb temperature, thermodynamic wet bulb temperature, and psychometric chart. So this is very important topic, how to refer a psychometric chart. So it is there are so many copies available in our library. You can please collect them, and you can borrow one chart, and it will be very useful for solving the problems in this unit. And then we have psychometric of air conditioning processes. So mixing of air streams. So these are the content in this unit, and then we are going to see the first topic, properties of moist air. So this topic we are going to see here in this session, and then we will move to Gibbs-Dalton's law in next session. So each session is a very simple topic only. So here, when you compare the content of unit number 4 with the earlier units, that is unit 3 and 4, this is very simple unit. We can easily complete in 9 hours. So I am planning to complete this in 9 sessions, and we are going to complete it in 9 sessions. Whereas in earlier units, each unit required 10 sessions, and we have done it. And now we are moving to unit number 3, unit number 4. So introduction to psychometry. So first I am going to introduce a few terminology which are very much essential in this unit. First, let me introduce what is psychometry. The psychometry is that branch of engineering science which deals with the study of moist air. So moist air is nothing but the dry air mixed with vapor, water vapor or humidity. So this is very important, and we are going to deal with the moist air here in this unit. And psychometry is that branch of engineering science which deals with the study of moist air. So dry air mixed with water vapor or humidity, that is known as moist air. So now psychometry is the branch of engineering with which we are going to study about moist air only. It also includes the study of behavior of dry air and water vapor mixer under various sets of conditions. So we are going to see different conditions also here in this unit. So though the Earth's atmosphere is mixture of gases including nitrogen, oxygen and argon, and also carbon dioxide CO2, yet the purpose of psychometry, it is considered to be a mixture of dry air and water vapor only. So we are not going to consider about other compounds which are like nitrogen, oxygen, argon, so carbon dioxide, whatever it may be, we are considering whole together as dry air and water vapor, so wetness in the air. So that we are going to consider here. So that is the psychometry. So first let us see what is dry air. So dry air is without vapor or without moisture or without humidity. So here the pure dry air is mixture of number of gases such as nitrogen, oxygen, carbon dioxide, hydrogen, argon, neon, helium, etc. So there are many compounds involved in this in dry air, but the nitrogen and oxygen have the major portion of the combination. So nitrogen is the major compound in the dry air. So I will show you the percentage. It is around 79 percentage, and the dry air is considered to have the composition as given in the following table. And you can see here these are the major compounds. So apart from this, we have many compounds, and they are in very small in quantity, and we are neglecting here. But if we see, the major contribution is from nitrogen. So it is by volume it is 78.03 percentage, and by mass it is 75.47 percentage, and molecular mass is 28. So this is 28, and here the oxygen O2 is 20.99. So it is around 21 percentage by volume, and 23.19 by mass, and molecular mass is 32. And argon, it is 0.94 percentage, and by mass it is 1.29 percentage, and by molecular mass it is 40 percentage. And argon, it is 0.94 percentage, it is lesser than 1, very marginally lesser. And if you see by mass it is 1.29 percentage, and we have 40 in terms of molecular mass. And carbon dioxide is, it is very low, it is 0.03 percentage, and by mass it is 0.05 percentage, and molecular mass is 44. And hydrogen, it is 0.01 percentage, and by mass it is almost negligible, and molecular mass it is 2. So this table, all of you please remember, and it will be very handy while solving the problems also. So to continue dry air, the molecular mass of dry air is taken as 28.966, and the gas constant of air is Ra. So it is denoted by Ra. It is equal to 0.287. So kilojoules per kg Kelvin, or 287 joules per kg Kelvin. So we can say in terms of kilojoules or joules. The molecular mass of water vapor is taken as 18.016, and the gas constant for water vapor is Rv. So Ra is the gas constant of dry air, and Rv is the water vapor, and it is equal to 0.461 kilojoules per kg Kelvin, or 461 joules kg per Kelvin. So joules per kg Kelvin. So this is just converted into joules. The pure dry air does not ordinarily exist in the nature, because it always contains some water vapor. So normally humidity will be there in air in almost all atmospheric conditions. The term air, so wherever used in this text, so means dry air containing moisture in the vapor form. So the term air is always a moist air, and it is considered to be mixed with what vapor. So both dry air and water vapor can be considered as perfect gases. So because both exist in the atmosphere at low pressure. So here both dry air and water vapor, so water vapor is wet air, and can be considered as perfect gases because both exist in the atmosphere at low pressure. Thus all the perfect gas terms can be applied to them individually. So the density of dry air is taken as 1.293 kg per meter cube at pressure 1.0135 bar, or 103.35 kilonewton per meter square, and the temperature is considered 0 degree Celsius, whereas 0 degree is when we convert into Kelvin it becomes 273 Kelvin. So this is the in terms of Kelvin. So these are the properties you should remember. So second one is moist air. So it is a mixture of dry air and water vapor. The amount of water vapor present in the air depends upon the absolute pressure and temperature of the mixer. So here the moist air is mixture of dry air and water vapor. It is a combination or mixture. The amount of water vapor present in the air depends upon the absolute pressure and temperature of the mixer. So mixer is nothing but air mixer. And next one is saturated air. So please remember all this terminology, and which is very essential while solving the problems. So next is saturated air. It is a mixture of dry air and water vapor. So here it is a dry air and water vapor when the air has diffused the maximum amount of water vapor into it. So when there is maximum amount of water vapor mixed with dry air, then that combination air or mixture of air is known as saturated air. So we cannot add further the water vapor, we cannot add further, so it is known as saturated air. Whereas in moist air, little bit of water vapor is mixed, whereas here the maximum amount of water vapor is mixed here with dry air. The water vapors usually occur in the form of superheated steam, as in the invisible gas. However, when the saturated air is cooled, the water vapor in the air starts condensing, and the same may be visible in the form of moist, fog, or condensation on cold surfaces. On cold surfaces, even we can see the droplets of water. So that is due to condensation process. Condensation is taking place there, and that water droplets is due to condensation, and that can be observed on any cool surface or surface of the container. So degree of saturation, it is the ratio of actual mass of water vapor in a unit mass of dry air to the mass of water vapor in the same mass of dry air when it is saturated at the same temperature. So here it is the ratio of actual mass of water vapor in the unit mass of dry air. So it is considered as unit mass. So that is important here. Please underline this, of dry air to the mass of water vapor in the same mass of dry air when it is saturated at the same temperature. So that is the degree of saturation. Next we have humidity. So we are talking about humidity everywhere. So this is nothing but it is the mass of water vapor present in 1 kg of dry air. So here this is very important, 1 kg of dry air. So water vapor that is there in 1 kg of dry air is known as humidity, and is generally expressed in terms of gram per kg, or dry air gram per kg of dry air. So it is also called as specific humidity or humidity ratio. So absolute humidity, so here it is the mass of water vapor present in 1 meter cube of dry air. So in terms of volume we are talking here, and is generally expressed in the terms of gram per cubic meter of dry air. So gram per meter cube. So here the gram per meter cube. So in humidity or specific humidity per kg we are talking about, whereas here gram per volume, so that is meter cube of dry air. It is also expressed in terms of the grains. So grains per cubic meter, so cubic meter of dry air, it is also it is also expressed in terms of grains per cubic meter of dry air. Mathematically, 1 kg of water vapor is equal to 15,430 grains. So that is the in terms of grains, not grams. So this is absolute humidity. So absolute humidity is treated or dealt in terms of meter cube volume, whereas humidity is specific per kg. So please remember this. So specific humidity, it is also known as the humidity ratio. So we have seen the humidity that is in earlier slide as a fifth point. It is the ratio of mass of water vapor per unit mass of dry air. So per kg in the mixture of vapor and air. It is generally expressed as grams of water per kg of dry air. So for given barometric pressure, it is a function of dew point alone, dew point temperature alone. So relative humidity RH, so it is also denoted as phi. So it is the ratio of partial pressure of water vapor in the mixture to the saturated partial pressure at the dry bulb temperature expressed as percentage. And now sensible heat, it is the heat that changes the temperature of a substance when added to or subtracted from it. So that is sensible heat. So it is the heat that changes the temperature of a substance. Next is latent heat. So latent heat, it is the heat that does not affect the temperature but changes the state of a substance when added to or subtracted from it. So it can change the phase or it can change the state of a substance. So that is the latent heat. So this is the heat responsible to change the one state to another state of that substance. Next is very important term, enthalpy. So enthalpy is the always we have seen enthalpy in earlier units also. It is the combination of energy which represents the sum of internal and flow energy in a steady flow process. So here the combination of energy which represents the sum of internal and flow energy in a steady flow process, it is determined from an arbitrary datum point for the air mixer and is expressed as kilojoules per kg of dry air. So in notation, if you see, it is notated by H letter, small h. When air is saturated, so dBT, WBT and dPT are equal. So that is dew point temperature, wet bulb temperature and dry bulb temperature are equal. So we are going to see what are these in coming slides. It is included in this unit. So relative humidity, it is the ratio of actual mass of water vapor in a given volume of moist air to the mass of water vapor in the same volume of saturated air at the same temperature and pressure. So here it is the ratio of actual mass of water vapor in a given volume of moist air to the mass of water vapor in the same volume of saturated air. So moist air, so volume of water vapor in moist air to the volume of the saturated air in the same temperature and pressure. So that is the relative humidity. So it is denoted by, or it is briefly written as RH, capital letters RH. Next, dBT, that is dry bulb temperature. It is the temperature of air recorded by a thermometer when it is not affected by the moisture present in the air. So this is the dry bulb temperature. So it is recorded by a thermometer when it is not affected by the moisture present in the air. So it can be considered as there is no moisture content in the air. And the dry bulb temperature, briefly written as dBT, is generally denoted by TD or TDB. So whatever it may be, so we are going to use dry bulb temperature in our calculations also. Next is WBD. It is nothing but a wet bulb depression. So wet bulb depression, it is the difference between dry bulb temperature and wet bulb temperature at any point. So it is the difference. It is the actual difference between dry bulb temperature and wet bulb temperature at any given point. When where the wet bulb depression is indicates relative humidity of the air. So here it is directly proportional, or we can say wherever we have this depression, and there we can say there is relative humidity in that air. Next is wet bulb temperature. So here air contains the vapor also. So it is the temperature of air recorded by a thermometer when its bulb is surrounded by a wet cloth exposed to the air. Such a thermometer is called a wet bulb thermometer. The wet bulb thermometer, briefly written as WBT, is generally denoted by TW or TWB. So we are going to see in the problems also. A WBD has its bulb covered with a piece of soft cloth or silk wick. So it is not normally a cloth and which is exposed to the air. The lower part of this cloth is dipped in a small basin of water, and the water from the basin rises in the cloth by capillary action and then gets evaporated. It may be noted that if relative humidity of air is high, then the air contains more water vapor. There will be little evaporation and thus lesser cooling of the bulb. So this is the way to measure wet bulb temperature. So this is the technique, or this is the direct factor with which wet bulb temperature having the variations. So it may be noted that relative humidity of air is high. So when the humidity is higher in the air, in that atmosphere, then the air contains more water vapor, then there will be little evaporation and thus lesser cooling of the bulb. So on the other hand, if the relative humidity of the air is low, so then there will be more cooling effect. So here the air contains less water vapor and there will be more evaporation and thus there will be more cooling effect. So this is what happening if the relative humidity of air is lower. So whereas here when the relative humidity of air is higher, then there will be lesser cooling effect, and when there is a relative humidity of air is lower, so in that case more cooling effect can be observed. So adiabatic saturation temperature, so next term, and this is another very important term you should remember. It is the temperature at which the water or ice can saturate air by evaporating adiabatically into it. So it is numerically equivalent to the measured wet bulb temperature as corrected if necessary for radiation and conduction. So that is the TWB. So it is the temperature at which the water or ice can saturate air by evaporate adiabatically into it. So adiabatically absorbs it. Next is DPT, dew point temperature. So dew point temperature is the temperature of air recorded by a thermometer when the moisture water vapor present in it begins to condense. So dew point temperature, where dew is nothing but the moisture content in it, and it is the temperature of air recorded by a thermometer when the moisture vapor water vapor present in it begins to condense. In the other words, we can say the dew point temperature is the saturation temperature Tsat corresponding to partial pressure of water vapor. So partial pressure of water vapor, that is nothing but PV. So it is usually denoted by TDP, and since PV is very small, water pressure of water vapor is very small, therefore the saturation temperature by water vapor at PV is also low, so less than atmospheric or dry bulb temperature. Thus, the water vapor in air exists in the superheated state, and the moist air containing moisture in such a form, so that is nothing but superheated state, is said to be unsaturated air. So this condition is shown by point A on the temperature entropy curve. So I will show you that in next slide. So that is TS diagram. So when the partial pressure of water vapor PV is equal to saturation pressure PS, the water vapor is in dry condition and the air will be saturated air. If a sample of unsaturated air containing superheated water vapor is cooled at constant pressure, the partial pressure PV of each constituent remains constant until the water vapor reaches the saturated state as shown in point B in the figure that is there in next slide. So here, if a sample of unsaturated air containing the superheated water vapor is cooled at constant pressure, the partial pressure PV of each constituent remains constant until the water vapor reaches the saturated state as shown in the next slide figure. So this is the diagram, TS diagram. So TDP equal to Tsat at dew point temperature and TD equal to T superheated. So at P at point A. So here these two, and this is the PV and this is PV, water vapor pressure, pressure of water vapor, and this is dew point and this is point A where cooling starts, and this is TDP and equal to Tsat at dew point temperature. So this is the simple TS diagram of dew point temperature. So at this point B, the first drop of dew will be formed, and hence the temperature at point B is called dew point temperature. So the temperature point B where the first dew point, that is the first droplet, forms. Further cooling will cause condensation of water vapor. So from the above, we see that the dew point temperature is the temperature at which the water vapor begins to condense. So here, this is the point where from here the condensation taking place. For saturated air, the dry bulb temperature, wet bulb temperature and dew point temperatures are same. So dew point depression. So in earlier we have seen dew point temperature. Now we will see the depression. It is the difference between the dry bulb temperature and dew point temperature of air. So psychrometer is, this is, there are many types of psychrometers, but the sling psychrometer is widely used. So it consists of dry bulb temperature thermometer and wet bulb thermometer mounted side by side in a protective case that is attached to handle by a swivel connection so that the case can be easily rotated. The dry bulb thermometer is directly exposed to air and measures the actual temperature of the air. The wet bulb temperature is covered by a wick, so thoroughly wetted by distilled water. The temperature measured by this wick covered bulb of a thermometer is the temperature of liquid water in the wick and is called wet bulb temperature. So already we have seen the working of wet bulb temperature measurement, and the sling psychrometer is the rotated in the air for approximately 1 minute. So after which the readings from both the thermometers are taken. This process is repeated several times to assure that the lowest possible wet bulb temperature is recorded. So this is the side by side. We have dry bulb temperature and we have wet bulb temperature, and this is the wet cloth covered here, and this is handle, and we can rotate this. We can rotate this through some angle, and this is known as sling psychrometer. So this is how the actual sling psychrometer is shown, and this is the actual one. There are digital psychrometers also available, and this is digital. Obviously, this is digital, and this is analog psychrometer. So here, this is an image of electronic psychrometer, metric measuring device capable of displaying temperature and humidity readings. So now it produces both humidity as well as temperature. Both it can show, and it is used for both WBT and DBT. So let me introduce the Dalton's law of partial pressures. It states, the Dalton's law is very important. Everyone should understand this. The total pressure exerted by the mixture of air and water vapor is equal to the sum of pressures which with each constituent would exert if it occupied the same space by itself. So this is the temperature, Dalton's law of partial pressures. So the total pressure exerted by the mixture of air and water vapor is equal to the sum of the pressures which, which each constituent would exert if it occupied the same space by itself. So this is the definition of Dalton's law of partial pressures. And in other words, the total pressure exerted by air and water vapor mixture is equal to the barometric pressure. So mathematically, barometric pressure of the mixture is equal to PB equal to PA plus PV. So this is the pressure of air and water vapor. So both are summation of both will give you the barometric pressure. So this is barometric pressure is nothing but the pressure measured by the barometer, where PB is the partial pressure of dry air and PV is equal to the partial pressure of water vapor. So this is PV and PB. And coming to the books, I recommend to read CP Aurora for entire unit, and it covers all the topics listed in this unit. So please refer CP Aurora, Refrigeration and Air Conditioning by CP Aurora, third edition. And Refrigeration and Air Conditioning by Rajput also gives you a few contents, and it also covers almost all the topics, but it is in the listed manner. Everything you can find in CP Aurora book, and you can also refer Kurmi book, and other resources are also available. And I suppose I have handed over all the materials which are required to read this subject in your through your Google Classroom. So we stop here, students. Please prepare well. We will be meeting in next session to discuss another topic in Unit 4. Thank you, students.